Today, Professor Piermarco Cannarsa from Propagation. Actually, his career, he finished his PhD in 1979 in the Scuola Normale, and then he became full professor at Propagation in 1990. And since on 2000, he was the vice president of England, and then currently he's the president of the Italian Mathematical Union. So his research focused on control for both BD, OD and PD, and also regularity theory from Jacobi equation, and recently from mean field game. So today he will talk about his book over 30 years on the propagation singularities.
Thank you, Kai. And thanks to all of you for being here. At the risk of repeating myself, I would like to express my gratitude for this invitation to visit this university and this department that I like very much. And also I am grateful for having the opportunity of talking about another subject, which is very important to me. As I said, it's been attracting my and other people's interest for over 30 years. So let me introduce the subject by a quote. In fact, this is from a 2016 paper by Kanin and Sobolewski, talking about the Hamilton-Jacobi equation, which is this object. It's a partial differential equation of the first order, only nonlinear, that appears in diverse mathematical models, ranging from analytical mechanics to combinatorics, condensed matter, turbulence, cosmology, and so on. And in many of these applications, the object of interest are described by singularities of solutions, which inevitably appear for generic data after some time. So this is a time-dependent equation, even if we give a very smooth initial condition, after some time, solution may develop singularities. And so one of the central issues, both for theory and application, is to understand the behavior of the system after singularities form, and also to try to describe the behavior of singularities once they appear. Okay, so I will give you sort of a historical tour to this theory of singularities, their estimates on singularities, propagation of singularities, mostly focused on propagation, in fact. So the object will be more generally a fully nonlinear first order partial differential equation, like this. And the H is what we usually call the Hamiltonian, by analogy with classical mechanics. And it's a sufficiently smooth function, and the important thing is that the dependence we get with respect to these variables, the gradient variable, is convex. So the object of the study is given a solution in a suitable class. I will comment this. Look at the points where the function u is not differentiable. So singularities means points of non-differentiability of the solution in this case. Typical examples of this situation are, Hamilton-Jacobi equations coming from mechanics, for example. The H is a function, is a smooth function, strictly convex in the gradient variable, and this is the time-dependent case. But also stationary problem, like the so-called eikonal equation, or variants of it, like they appear in weak KM theory, where they have eikonal equations depending on possible additional parameters. Okay. So, anyway, the object is the study of this set points of non-differentiability. Before we get into more technical details, let me give you a visual approach to singularities. They go through the distance function, which is another thing that will occupy a lot of space in this talk. So we have a set. In general, distance function, the Euclidean distance function is just the infimum of distances of a point x from any point of S. If we take for S the boundary of a certain two-dimensional domain, called sometimes the table, then the distance to the boundary describes the equilibrium configuration of a sand pile. If you pour sand on a table, well, it will start forming a pile, and then it will touch the boundary and start falling from the edges. But at an equilibrium configuration, the profile of the sand pile is essentially the graph of the distance to the boundary, multiplied by some constant that depends on the material. So you see, so here we see the singularities of the distance function, which is also a solution of a Hamilton-Jacobi equation, because you know that the distance function, where it is differentiable, has a gradient which has norm 1, so the typical equation would be norm of the gradient of the distance equal to 1. And you see that, well, singularities show on the graph. Of course, when the table is non-smooth, you get singularities that touch the boundary. But even in case of smooth tables, smooth open domains, well, in the neighborhood of the boundary, the distance function is smooth, but at a certain point, a singularity develops. Okay, so one of the reasons to analyze the singular set of the solutions of this equation more closely is that, well, it's exactly on the complement of this set that you can have the classical method of characteristic work. It is one of the classical methods, very classical, to study first-order nonlinear PDEs, is through the so-called characteristics, which is this system of ordinary differential equation, starting from the manifold where you give the initial condition, in this case is Rn and t equal to 0. And by solving this system, you can reconstruct the solution of this PDE when and where it is smooth. When and where it is smooth, it means on the complement, not just of the singular set, but of the closure. So, if we can say something on the closure of the singular set, we can be sure that on the complement of this set, the solution, for example, has exactly the same regularity as the data U0 and H. If U0 is CK, the solution is going to be CK, and so on. Maximal regularity for this kind of problems. Another reason I'm interested in singularities is that there is a connection with optimization, in particular with the classical calculus of variation or optimal control, depending on the kind of Hamilton-Jacobi equation you are considering. For example, if we have this problem. If we consider the Lagrangian associated with the Hamiltonian H, and if you look at the functional of the calculus of variation given by the integral of the Lagrangian plus an initial cost U0, exactly the initial condition here, and you minimize this function along all arcs which end at x for time t, so the infimum of this problem is exactly the viscosity solution of this PDE. I'm not going into the definition of viscosity solution. Let me just say that as we know, in general, solutions are non-smooth. Solution of first order nonlinear PDEs are not smooth, but one is interested in selecting along all possible non-smooth solutions the ones that are physically meaningful, or the one. And this was one of the major achievements of the theory of viscosity solution, to give an abstract definition of how to select among all possible, almost everywhere solutions, the solution which, for example, realizes the minimum of this function, the value function. Okay. So there is this deep connection between Hamilton-Jacobi equation and optimization, and within this connection, differentiability or not differentiability as a variational interpretation, in particular at points of differentiability for the solution of this equation, you can be sure that this minimization problem has a unique solution. So there is a unique minimizer. And at points of non-differentiability, therefore, you have several minimizers. And if you understand well the structure of the solution, about the point of non-differentiability, you can say many things on the structure of minimizers, of the calculus of variation, optimal control, or whatever other problem you are considering. Okay, so this was the introduction, and this will be the topics. I will try to touch at least the first four. Let's see if I get to the fifth one. So I said I will give a historic tour, so we start from the beginning. In fact, at least for the beginning of my personal involvement in the problem, which occurred back in the late 80s, in fact, at Brown University. This is the division of applied mathematics, where I was sort of postdoc, but in fact there was no doc in the year before. So postdoc fellow at Brown University, visiting Wendell Fleming. And that's where, well, I met Mete Soner. And this is the first paper we wrote with Mete on this issue about singularities. As it always or often happens, in order to make progress in, well, studying solutions of PDEs, it is useful to have a functional analytic tool. In our case, it was the use of semi-concave functions, which are functions that generalize the notion of concavity, all in a very easy way, essentially with respect to the typical concavity inequality. We add an error term, which is of order strictly greater than 1 with respect to the oscillation of the independent variable. And this order greater than 1 is measured by a modulus, which is a function omega that you see here. So if omega is 0, you recover concave functions on all convex subdomains of omega. When the modulus is linear, you recover the so-called linearly semi-concave functions, which are the most used, in fact. And very easy also to introduce, because any linearly semi-concave function can be easily represented as a sum of a concave plus a smooth function. But also fractionally semi-concave functions are important, which amounts to having a fractional modulus. Sometimes you cannot get linear semi-concavity, but still with fractional semi-concavity, many of the properties of these functions are true. Well, there is a huge amount of work on the non-smooth analysis, control theory, and so on that uses semi-concave function. Let me just skip the references because we have a lot of way to go, a long way to go. Let me just stress the fact, a couple of notions that will be useful to recall. So a semi-concave function, like a concave function, is locally Lipschitz. So it's a function which is differentiable at many points. The points of non-differentiability of a semi-concave function measure 0, Lebesgue measure 0. It can be a mess, but it has a set of Lebesgue measure 0. Therefore, at each point x, you can find, well, many clustered points of the gradient. The gradient is locally bounded, being the function locally Lipschitz. You can find many sequences of nice points where the corresponding gradients have a limit. So you recover all these limits of possible gradients, and these are the so-called reachable gradients. It's a closed set that I will denote by this star. So at the point of differentiability, this star is a singleton. At the point of non-differentiability, this star has many, many elements, but it's a compact set. In general, it is not convex. And if we convexify this set of limiting gradients, we find, well, what in the literature is known as a Clark gradient, which coincides with another object, which I'm not going to introduce, but it's called the superdifferential when the function is semi-concave. So for a semi-concave function, all these notions of gradients are more or less equivalent, but Clark gradient is attached to this D plus, which means somehow approximation from above to the graph of the function. So a semi-concave function looks roughly like this. It may have singularities, but singularities have all a sort of concave behavior, and you can support either plane to the graph from above at every point. These support hyperplane are related to the superdifferential or the Clark gradient. So since this is a convexification, this set is convex. Since this star is compact, this set is compact. So the superdifferential of a semi-concave function is in general a convex compact set, non-empty. When it is a singleton, the function is differentiable. And we are exactly interested in the set where the dimension of this T plus is greater than or equal to 1. That's the singular set. One last thing. When we restrict the attention to semi-concave solutions of Hamilton-Jacobi equations, when U is semi-concave, then the property of satisfying the equation almost everywhere is in fact equivalent to the viscosity property. So viscosity solutions have to satisfy certain constraints at every point in general, but if U is semi-concave, it is enough to have a sort of almost everywhere. The equation holds almost everywhere in the domain. And there is also another thing to stress, is that when U is a semi-concave solution, then we have a sort of a quantitative index of singularity. A point is singular if and only if the Hamiltonian is strictly negative on the superdifferential at this point. So, well, it's strictly negative, the minimum of the Hamiltonian is strictly negative. So, the equation is satisfied almost everywhere. At points of differentiability, this set is not a singleton, it's a superdifferential where I recover all possible cluster point of gradients. And in fact, when I minimize on this convex set, a convex function, which is the Hamiltonian, this minimum has to be strictly negative if the set is not trivial, if the set is associated to a singular point. Now, going historically, this is the sort of first result on propagation of singularities, but it didn't look, so this is the result back in 1997 at Brown University, although it didn't look in the formulation as a real result on propagation. It was saying the following: you take a Hamilton-Jacobi equation of the time-dependent form with H, as I said, strictly complex and smooth. You take a solution, a semi-concave solution. If you know, and you fix a point, not x naught, if you know that above this point, on an open cylinder, the solution is C1, then it must be C1 also at the base, at T naught. So, it was a very, well, it was an understatement to say that if you have a singular point, that it must somehow propagate forward in time, at least along some sequence. And then there were many questions that originate from that first result. And we will see where all these questions brought the analysis. So the first attempts we made was to sort of bound this singular set from the measure theoretical point of view. So we are talking of a set of Lebesgue measure 0, but Lebesgue measure 0 may mean well, 10 sets, whatever, no structure. So we were trying to find a tool to say more. And it turned out that a good tool is some geometric measure theory, the notion of rectifiable sets. And in fact, one can show is that if you have just a semi-concave function, here there is no equation, just start from the semi-concavity property, then you can say that the singular set of a semi-concave function is countably n-1 rectifiable. So it means it can be covered by a countable family of Lipschitz graphs of dimension n-1, of Lipschitz function defined on a space of codimension 1 with respect to the ambient space. And in fact, you can say more if you stratify the singular set according to the dimension of the superdifferential. So this is an integer ranging from 1 to the top dimension, if you look at the singular set. And, well, the higher the index, the smaller the corresponding singular set. Singular sets of magnitude j, where the dimension of the superdifferential is j, are countable n-j rectifiable. It means they are covered by graphs of dimension smaller and smaller as j goes on. When j is n, the top dimension, singular sets of top dimension are just countable sets. 0 rectifiable means countable. And also, so these results were partly known in the case of concave function and then extended to general semi-concave function in collaboration with Ambrosio and Alberti that you see here. Okay, so this is for general semi-concave function. You can bound the singular set better than just saying Lebesgue measure 0, you can say rectifiable. What if I add the extra information that U is a solution of the equation? Okay? So now I take a semi-concave function which, in addition, solves, for example, a time-dependent Hamilton-Jacobi equation, just to go historically. Then, as we said at the beginning, we know that on the complement of the closure of the singular set, we recover the same regularity as the data. For example, if you notice ck plus 1, h is ck plus 1, we can obtain the same regularity on U. But what about the closure? I mean, having the rectifiability estimates on sing U doesn't say much about the closure. You can have a rectifiable set, then you close it, you find a big thing. So the problem was already studied by Fleming in '69, where singularities were not so much associated to points of non-differentiability of the solution of the Hamilton-Jacobi equation, but rather at points where the value function of the corresponding calculus of variation problem had several, I mean, the minimizers were more than one. And, well, in that case, he proved that the closure of the singular set is contained in the set, in the union of the singular set itself, plus an extra set, which is important in calculus of variation, set of conjugate points. I'm not going into the definition here, just what you have to add to singular points in order to catch the closure. And by just, but they have also a characterization in terms of points at which certain determinants become singular, or certain transformation, and so they allow application of Sart's theorem which well, gives this kind of estimate. H is the Hausdorff measure in dimension n plus 1 over k. So we are in dimension n plus 1 because we have n space plus 1 time dimension. And this is what SAR gives. This is not enough to recover any rectifiability information because n plus 1 over k is greater than n. And so. On the other hand, it turned out that one can take a closer look at the set of conjugate points. And, well, I'm not going to explain the proof, but you can prove that the set of conjugate are better than what just SAR gives. SAR never gives the optimal estimates. At some point, you are forced to apply SAR-type reasoning, but you want to do it as late as possible. So recover many more information before addressing the problem by a SAR-type argument. So if you do that and you perform a certain analysis of the set of conjugate points, you can actually find out that this set is HN rectifiable. Means that away from a negligible set for the Hausdorff measure, it's covered by a countable union of n-dimensional graphs. Therefore, this ensures that the closure of the singular set is HN rectifiable. And in fact, you can even prove that that the points which are conjugate and non-singular that you have to add to the singular set in order to obtain the closure have even codimension 2, at least in the case of smooth data. Okay, this was back in 1997. Then it was extended to other, this was for time-dependent Hamilton-Jacobi equation, it was extended to stationary Hamilton-Jacobi equation, and so on. But that completed somehow the analysis of the singular set. As for upper estimates from above, measured theoretical estimate, you cannot do better actually. These are optimal estimates in the sense that you can produce examples where exactly you find this kind of singular set rectifiable of codimension 1. So we were quite satisfied with that. So we started looking at the opposite point of view. Like, can we bound from below this singular set, saying that if I start from a singular point, well, that is not isolated, but at least when the equation has some structure, singularities propagate, and where do they go, and so on. Somehow in the flavor of the initial quote by Gannon. So, of course, there are examples of concave functions, like this one, where singularities propagate along straight lines. We are in dimension 2 here. But there are also concave functions with isolated singularities, like a function like this. Of course, a trivial example of a concave function with an isolated singularity is a cone. But this example is even more interesting because so it's a function essentially like the square root of x squared plus y to the 4th minus. This is more interesting because this function has an isolated singularity at the origin where the superdifferential is one-dimensional, unlike the cone, which is a cone. So what is the criterion to decide about propagation? It cannot be the magnitude. And if we look at go back to the first example, one could think, for example, that singularities of magnitude 1, like the one you find on the axis, propagate, because the magnitude is not the top one. Whereas here you see you have a singularity of magnitude 2, which remains isolated. On the other hand, we know that singularities of top magnitude can be a most accountable set. But no, magnitude is not the right criterion, because here you find a singularity of magnitude 1 over 2 that remains isolated. It turns out, we go back to the first example, that what makes the difference is the distribution of the reachable gradients at a singular point on the boundary, on the topological boundary of the superdifferential. One can show that reachable gradients always stay on the topological boundary of the superdifferential. And in this case, good case from the point of view of propagation, at any singular point, where you are on these lines, or when you are at the origin, where the superdifferential is two-dimensional, the reachable gradients are the points that span the superdifferential. So in this case, they are the four corners. Here they are the two endpoints. But they do not cover the whole topological boundary. They leave room in the topological boundary. And it turns out that this is a sufficient condition, in fact, for having propagation of singularities. If you have even for a simply semi-concave function, if you have a semi-concave function with a singular point on which for which you can find room on the topological boundary which is not covered by reachable gradients, then you can find essentially a Lipschitz arc starting from the point, which is all made of singular points, which is non-trivial because it has a non-trivial tangent at the initial time, and for which you can even give a sort of description as a solution of a certain inclusion. Okay. So this was sort of unexpected when we realized that even for a semi-concave function you can give a sort of dynamics governing singularities. And then one asks what you can do in case your semi-concave function is a solution. Maybe you can relate, you can find other conditions that ensure the validity of the geometrical condition that was imposed in this result. So it turns out that in case of solution, an object which is central to the propagation of singularities are characteristics, generalized characteristics. So we saw what the characteristics are in the classical case. In when the function u is not differentiable, you have to interpret characteristics in a relaxed way. So you replace u by the superdifferential. Then you consider the transformation of this set to this nonlinear map, the gradient of the Hamiltonian. And then that's not enough, in fact, because there is a well-established theory of differential inclusion. So it extends the well-known theory of ODEs. But in order to have existence of solution, you have to have some properties on these objects. And one of the properties is that these sets, where the derivative has to belong, should be convex. Otherwise, general theory does not apply. So in order to have this convexity, which is not preserved in general, even if this set is convex, when you apply nonlinear transformation like that, you may lose convexity. So we add a second convexification here, which is good from the point of view of existence of solution of these objects, less good from the point of view of uniqueness, because you have somehow enlarged the constraint. So in general, solutions to differential inclusions like that are not unique. However, for certain kinds of Hamiltonians, like for the eikonal Hamiltonian, quadratic Hamiltonians, which is important for the distance function, when you take the gradient, this is just the identity, and so this convexification becomes useless, and you recover uniqueness. So for a eikonal type and more general Hamiltonian of a Riemannian structure, you can show that there is a unique generalized characteristic starting from a given point. And this is not hard to show, in fact it's embarrassing. It's very easy to show, but as soon as this condition fails, we know nothing about uniqueness, essentially. So when you have a quadratic or a Riemannian and Newtonian, essentially these generalized characteristics coincide with the generalized gradient flow. And since U is semi-concave, you take two solutions. It turns out that you can bound the derivative of the square of the norm, of the difference, by using semi-concavity, by the function, the square of the norm itself. This is an inequality that follows directly from the semi-concavity property of U, which is semi-concave. So the semi-concavity property of U. And then you apply Glombal's lemma and you get this. So it's very easy to show that there is a unique solution when H is quadratic, and we know nothing about uniqueness when H is not. Well, we know that in general, there is no uniqueness, in fact, because of this double convexification. So people try to restrict the notion. They introduce so-called broken or strict characteristics by just deleting the second convexification. Then it is not easy to show the existence. It's really, it takes a refined analysis, and you have to know a lot about the function U and H. But still, Cunningham and Sobolewski obtain an existence result for this notion of strict characteristic. They also show that the selection of the superdifferential that enters the characteristic inclusion minimizes the Hamiltonian. But again, so in some sense, there is a unique velocity for this strict characteristic. But that's not enough, of course, to guarantee the uniqueness of the solution of the Cauchy problem for a fixed initial condition. So that's one of the major, an interesting question in the theory. Can one show that strict characteristics are unique? This would have a lot of interesting consequences. Anyway, what do characteristics have to do with propagation of singularities? Well, one can show that if you now have a semi-concave solution of a Hamilton-Jacobi equation and a singular point, which is not critical, such that 0 does not belong to this set. And this is just to avoid trivialities. I mean, trivial result. Then you can, again, as in the previous result with Albano, you can find a Lipschitz arc, which is made of singular points, starts from an x0, and such that, it has a non-zero derivative at t equal to 0, and this is why we require this fact, because we don't want 0 to be set so that this derivative is non-zero, so it actually moves. It's not a constant arc, and in fact it captures the minimum point of the Hamiltonian. And for solutions, you give a criterion without having to know the structure of the superdifferential. You just have to know that the point is not a critical point. And of course, you can apply strict characteristics, which are special cases of generalized characteristics, and give other versions of this. So notice that in this result, the theory is local. You ensure the existence of a shock for a certain time, tau, which may be very small. Now we want to see when we can say something on this tau. When can we say, for example, that tau is plus infinity? The question seems academic, but it has application to other domains. For example, to topological issues. Now let's go back to the distance function. Distance from the boundary of an open domain. So we have an open domain inner n, bounded, and we take the distance to the boundary. As we noticed in the send file before, in this case, the singular set is always there. No way that the distance function can be smoothed all over. And here it's pictured in red. It is called sometimes the ridge, the medial axis, and it coincides with the set of points where the metric projection is multivalued. Where points that have more than one projection onto the boundary. So, in one question one could raise is how much I recover of the domain omega if I look just at the singular set of the distance? How many properties I keep? In mathematical terms, for example, are omega and sin t homotopy equivalent? So this question was raised well, by people working on computer graphics, because they have the problem of storing data. And of course, data occupies space, and they want to reduce the complexity of the objects. And so somehow looking at the singular set of a two-dimensional object lets you pass from a two-dimensional object to a one-dimensional object. And so one idea to address this problem is, okay, I see the singular set as a retract. So I start from a point where the function is differentiable. I follow the flow of the gradient. At some point, I have to meet the singular set, and I stay there. So I see the singular set as a retract of omega, and I get the homotopy equivalence this way. So it turns out that this strategy works, but not always. It requires either some smoothness, so the boundary of omega to be C2, or low dimension, two dimension, and then it works when the boundary is piecewise C2. Otherwise, you may lose the continuity of this retract. One example would be this. I don't know if it is easy to. So forget about this wall at the beginning. This is the interior of a box, and that's the set omega. And the singularities move along these planes. They fill the room in this way. And that's okay. But if I dig a hole like that, then I create a new bunch of singularities, which are these ones. And along these edges, the projection, the retraction technique becomes discontinuous. Because I can get at a point here, the retraction technique takes me there, but if I then touch this singularity, I destroy the computer. So, what can we say? The homotopy equivalence is only true with sufficient smoothness? Indeed, no. So one can show, this is result by Jacobi, that it always takes place. It's always the case, and omega is always the same homotopy as the singular set. And the proof in this paper is quite elaborate. It's elementary, but being elementary has to go through all the computation you can imagine. One simple proof can be proved if you suppose to be able to construct a generalized gradient flow, solution of this differential inclusion, for all times, such that once you meet at a certain time t0 the singular set, psi stays on the singular set forever. Because in that case, you define the homotopy very easily. First, you show that for n there is a sort of common time, capital T, such that your flow must meet the singular set. And then with this rescaling, with this uniform time, you define this function h in this way by just using the flow, the generalized gradient flow, and that gives you the function to construct the homotopy. So the question becomes, when can one show that this sort of global propagation result, that when you can solve your differential inclusion in such a way that when the solution becomes singular, then it stays singular forever, not just for a short time, as in the result I showed you before. So the first result on global propagation, in fact, was this one, and I guess you know this guy. Again, the banner is this guy, and exactly says that what we needed for the application. That if you consider the distance function to the boundary of an open domain, no assumption of the regularity of the boundary, and you consider the corresponding generalized gradient flow, then global propagation occurs. Once, if you start from a singular point, you stay singular for all time. It's clear that these solutions are defined for all time, because the right-hand side is bounded, but it's not clear that that you preserve singularities for all time. And that was the contribution of this result. So now, 5 minutes more.
Well, you have, let's say 5 minutes.
Less.
No, 5 minutes.
Okay. So, once you get this result in the case of the distance function, of course you ask what happens for general solutions. I mean, how can I interpret this global propagation and the application of the topology in a more general environment? And so, one way is to look at in general, we go to a Riemannian manifold. We can go to a connected compact, but not necessarily compact, Riemannian manifold. And we take a solution of a stationary Hamilton-Jacobi equation. These are sometimes called Wickham solutions because they were developed essentially by Albert Fati, but they are equivalent to viscosity solutions. And so they may develop singularities and so on. So now we want to find the analog of the previous result with the domain, with the homotopy equivalence between the singularities and the domain itself. So we have a solution here, we have a manifold, so we have the singular set of the solution. What is the other actor of this homotopy equivalence? What is the singular set homotopy equivalent to? So in order to understand that, one has to introduce the Aubry set. So the Aubry set, in order to introduce the Aubry set, one has to introduce calibrating curves or absolute minimizers. So you are given a solution of this equation. You have H, you have L, the corresponding Lagrangian, and you say that a curve, defined on AB with values in them, is calibrating if, when you integrate along this curve the action, the result is just the variation of u at the extreme points. There is an equality here. Whereas in general, solutions with respect to curves satisfy an inequality. So, calibrating curves somehow, well, they play the role of minimizers in calculus of variation. Sometimes they're called absolute minimizers. And the Aubry set of U is exactly the set of points that belong to a calibrating curve which is defined from minus infinity to plus infinity on the whole line. So essentially these are the points of a global calibrating curve, global absolute minimizer. One can show that this set is non-empty. So one can introduce the set of cut points of U, which morally are the closure of the singular set. But let's concentrate on the Aubry set. Aubry set gives us exactly what we needed to understand the homotopy mechanism. The singular set is contained in what is this? Is contained in the complement of the Aubry set in the manifold, because the Aubry set is made of nice points which are in the interior of a calibrating, of a global calibrating. So the conjecture is that the homotopy equivalence takes place between this set and this set. And in fact, that's true. That's the result we had with Wei Cheng and Alpha T and many other results. So the singular set is homotopy equivalent to the complement of the Aubry set, and in fact, all these other sets which are nested in this way, these are not homotopy. The technique is, well, ideally not very different from the one we saw at work for the distance function, but, well, the idea, but the technique is much more involved in this case. One has to construct a function h on the complement of the Aubry set cross 0, 1 into itself with certain properties in order to build up this homotopy. Of course, it has to be the identity at t equal to 0, it has to send at t equal to 1 the whole space into the singular set, and for each time it has to leave the cut set or the singular set, we are not interested in the cut set, X. So the basic tools to get that are the so-called, well, it's in fact Laxonenic operators. These are two objects that are used in weak camp theory. This one gives you a solution of a time-dependent equation. This other object, the positive Laxonenic operator, in fact, can be, gives another kind of solution. But the interesting thing is that this supremum is obtained. This is the action related to the Lagrange. And the points of maximum of this difference are exactly the points used to build up the homotopy. And in fact, singularities propagate along these maximizers. Okay, this is not much, but just to stress the connection between the analysis of propagation of singularities and the construction of these homotopies. Okay, so this has also applications, well, to similar issues. Like, for example, if you look at the set of points on a manifold that can be joined by unique minimizing geodesics, and you call it U, and the complement of this set, which is the points which are joined by at least two minimizing geodesics, and you call this second set N of U. N of U is another complicated object, but one thing that one can realize is that in fact this is nothing but the singular set of the distance in the product manifold, n times n, to the diagonal of the product. And then one can apply the previous result to obtain that this set, where the geodesics are not unique, is homotopy equivalent to the complement of the diagonal in the product. So, somehow, to conclude, well, in these 30 years, the analysis, as you see, has well, developed from the 1987 result to many different descriptions, and some results that seemed impossible to obtain. Nevertheless, there are still many questions that one would like to understand, like the uniqueness of the characteristics, or what happens for more general Hamiltonians than the ones I used in this talk. So somehow this is a sort of a long history going on. So I like to compare it to this other object where history. So this is not campus in Raleigh. This is from Rome, and somehow reminds me of the long path we have gone through from the beginning. So thank you for your attention.
Are there any questions?
So,
Yeah.
how you relate your result for the singularities in shocks of the conservation law?
Well, they are exactly the same in dimension 1.
Yeah, I know. I'm interested more in general.
In dimension 1, is they are the same. In,
There's non-convex case. So
yeah, that would be, we have no results in non-convex case here. But again, in conservation law, you have in dimension 1. So that's one of the important issues to address, non-convex and convex. Yeah. You miss semi-concavity in the solution in that case, so you will have to replace this property with something else. Of course, in dimension 1, you have viscosity solutions or entropy solutions, so you can import the theory of conservation laws. When you go up with the dimension, that's one of the major problems.
Other questions?
So to move beyond semi-concave, what do you have in mind?
Beyond.
Yeah. They might be used with other kernels, right?
Yeah.
Because it's where-
Well, I mean, if you stay in the convex framework, convex and convex, semi-concavity can be generalized in several ways. One of the ways is you look at the hippograph of this function. If you can say that this hippograph has an exterior sphere condition, you can recover a lot of properties of semi-concave functions in more general frameworks. For example, that property does not imply local Lipschitz continuity of the function, but still gives you a second-order Taylor expansion almost everywhere. All this was studied by Kai and partly by Gonda and also. But if we go out of the convex framework for the Hamiltonian, so we consider non-convex Hamiltonian in the area. So that's.
Other common questions? Well, I can comment on the question a bit for the question of gas. Because for conservation law, when you have the strictly convex, and then you have only the estimate and related semi-concave. Okay, forget about the non-convex case. Just do convex case, but not really convex. The solution does not have an estimate, not in BV. But the way of the people from conservation law, they think, they look at the solution along the characteristic, the speed, F prime. And then that's why it's still BV and capture something of the semi-concave. And then the work of the conservation is time to go back to for Hamilton propagation and move to decay. That technique cannot be used. So the question is, in general, well, you look at the gradient solution along the gradient flow, like the gradient Hamiltonian, what irregularity is happening. It's hard question. But we try to improve the thing from conservation law to Hamilton equation. So you mean that whether the gradient of the Hamiltonian and the gradient solution is precisely the F prime of the solution of conservation law. Again, some regularity. It's not easy for even in the convex case. Even in the convex case. Okay, any other questions?
Let me just one last remark. So on 26 or so, you had an issue with non-uniqueness of these characteristics, right?
Yeah.
Potentially, right? So can't you just, I mean, typically you put down or take the lazy solution, maybe, the one of minimum norm, or the one that would satisfy some kind of rational principle, and this one you have interesting properties.
You would imagine that the strict solutions, strict characteristics were unique, because somehow they minimize at each time, they minimize the Hamiltonian and the super differential. They are all what you require a priori for uniqueness, but nobody has shown uniqueness so far. Except for, again, very special cases. Of course, when the Hamiltonian is quadratic, then you fall into the case I showed you. Another case where you can prove uniqueness is in one space dimension plus time, because in that case, the action of the Hamiltonian is a scalar function, and then you can use semi-locality again. But otherwise, I don't know. I don't know if they have a lot of nice properties, but I don't know I find it a very interesting problem. Very interesting. If they were unique, you could probably reduce a lot of nice consequences.
Any other questions? Otherwise, let's thank Piermarco again. So Piermarco will stay until Thursday, so if you want to discuss in this room,